So the second half of Test 2 is going to come from material covered in Chapter 20, which is our first of 3 chapters covering different aspects to the cardiovascular system. Now we did temporarily jump over Chapter 19, which is blood. And the reason we did that is to kind of go a little more in line with the order at which the lab goes. And the lab course does cover the heart after the endocrine system and puts the blood at the end of the cardiovascular section. So we're going to do that. The heart works as the muscle of the cardiovascular system. Cardiovascular system as a whole functions to transport and deliver substances throughout the body, both good and bad. As such, it's got to have something be the force that delivers, makes the blood move. The blood itself, of course, is the delivery mechanism, how we transport substances throughout the body, and then where that blood is directed to go is determined by your blood vessels. So we're going to talk about the heart's function here with this chapter here. The heart itself is an extremely impressive organ, in my opinion. It never gets a break. It is constantly working throughout your life, and on average, based on what we know, it's going to pump about your entire volume of blood per minute. And that's a resting rate. That's you sitting around doing nothing, watching some Grey's Anatomy. That's the rate at which your heart pumps blood. That number can double, almost triple in times of exercise or things like that. So the heart is an incredibly awesome organ to be able to accomplish that. If we took this in totality, your heart would pump about a million gallons of blood per year. And that million gallons of blood is being forced through 60,000 miles of blood vessels. So not only does this have to continually work, it has to create enough force to make sure the blood gets to all the nooks and crannies of your body. So this is a pretty impressive organ to be able to do all that. So let's take a closer look at its anatomy and its physiology so we can maybe try and understand how it accomplishes that job. So as you recall from A&P1 when you did your general overview of anatomy, of the organ of the body, the heart itself is in general is located in your thoracic cavity within the mediastinum. The mediastinum being the central kind of core to the thoracic cavity. The outer portions, the lateral portions, are of course filled with the lungs. The heart itself sits somewhat in the center of that mediastinum, but it does kind of sit off askew, sitting off to the left side of the thoracic cavity. It also tilts slightly forward. This causes the heart to have a unique arrangement, so to speak, and some identifying characteristics, or identifying ways. There's some unique ways in which we identify different aspects to the heart. So here we have the right border and left border, obviously. The inferior surface sits across the diaphragm, not to be confused with the base. The base is actually this posterior border to the heart that rests against the vertebral column. Then we have the apex to the heart. Now, apex means point, which is going to be this area here where the heart comes to a point. This will, of course, make more sense when you're actually looking at a heart in lab, but hopefully you guys can get a general idea here from these pictures. Now, a lot of students get confused with apex because they think apex means top, but that is misconstrued. Apex means point, but it's often misused as top, since most things that have a point have it on the top, so it kind of gets misused in that way. The heart itself is surrounded and anchored in place by a pericardium. Pericardium, very important membrane for this function. The pericardium itself has 2 layers since it is a serous membrane. Looking at this, we have the outer layer that lies away from the organ, which is your parietal pericardium, the layer that lies directly on top of the organ, which is your visceral pericardium. The visceral pericardium, also referred to as the epicardium. And then we have this space in between. Now that space in between is going to be your pericardial cavity. Now note the pericardial cavity surrounds the heart but does not actually contain the heart. It's an important distinction to make, because what we see is we have our parietal layer, our visceral layer, then we have the heart. And, or let me rephrase that. We have the parietal layer, then we have our cavity, we have our visceral layer, and then the heart. So this cavity is described as surrounding the heart but not containing the heart. Important little distinction there. This arrangement creates this fluid-filled sac that surrounds the heart that offers a couple of important functions. It offers a certain amount of cushioning for the heart within the thoracic cavity, but most importantly it offers friction reduction, because inside of this pericardial cavity is going to be pericardial fluid or serous fluid. The serous fluid is got a oily type feel to it, and what it does is allows the parietal and visceral layer to slide past one another relatively easily with very little, if any, friction. This, of course, is beneficial because every time the heart beats, it's going to rub, and we don't want the heart developing blisters since it doesn't ever get a break. Taking a look at the heart wall, we're going to see the heart is composed of 3 layers. You have the outer layer here, which is your epicardium, and remember the epicardium is synonymous with the visceral pericardium. They are interchangeable. Then we have the middle layer, which is your myocardium. So this M is not only for middle, but it's also for muscle. The myocardium is made up of your cardiac muscle, and it's the muscular, where we would find the muscular component to the heart tissue. And finally, we have the inner lining here, which is your endocardium. The endocardium is continuous with the endothelium that lines your blood vessels. And it is simple squamous epithelium. Now, in your capillaries, this simple squamous epithelium is, of course, going to be useful for capillary exchange and diffusion. But here in the heart, it's not necessarily important for diffusion. So why do we have this simple squamous epithelium? Well, we have this simple squamous epithelium lining your heart and all of your blood vessels because it also is beneficial to offer a very smooth surface. And the smoother the surface, the easier it is at which blood can flow, and the less friction there will be when the blood rubs up against that vessel wall. And of course, if all of that is true, then it's going to take less effort to pump the blood throughout the body, which is of course beneficial for that heart. Taking a closer look at the external anatomy of the heart and the organization of the heart as an organ, what we see is the heart is broken into 4 chambers, 2 upper atria and 2 lower ventricles. Now, externally, those 4 chambers can be identified or differentiated via grooves that are found on the surface of the heart. You have 2 sets of grooves. You have a coronary sulcus, which encircles almost the entire heart, and it signifies or demonstrates the border between the upper atria and the lower ventricles. Now, and then leading or extending away from the coronary sulcus almost perpendicularly, we have the interventricular sulcus, which extends from anterior to posterior, being divided into the anterior interventricular sulcus and posterior interventricular sulcus. And as the name implies, this groove is used to differentiate the right ventricle from the left ventricle externally. Now you might ask, what differentiates the right atrium from the left atrium? Well, that is differentiated or separated via the great vessels that extend out the aorta, extend out the heart, including the aorta and pulmonary trunk. Now these grooves not only serve to signify the borders between the chambers, but these grooves also contain the larger coronary blood vessels that then branch off to feed the heart. Internally, when we take a look at this, we still, of course, see our chambers, but we find some additional structures. Now, the right side of the heart is what we see here. It is going to receive blood from systemic circulation. Okay. So the 3 sources that drain into the right atrium include the superior and inferior vena cavas, and then also the coronary sinus. Now, draining into the right atrium is going to be deoxygenated blood from systemic circulation. Now, this deoxygenated blood from systemic circulation moves from the right atria through the tricuspid valve into the right ventricle. Now, the tricuspid valve is a three-cusped valve we see here, possessing these chordae tendineae and papillary muscles, which allow it to function properly, and we'll see that shortly. Once in the right ventricle, we see that the chamber consists of quite a bit more muscle mass than compared to the atrium. Internally, we see a variety of characteristics. We see these little ridges and valleys down here, which is going to be your trabeculae carnae. And a few of these trabeculae carnae are quite enlarged, as you see here. These enlarged trabeculae carnae are going to be your papillary muscles, and these papillary muscles then attach to the valves. The papillary muscles, along with the chordae tendineae, attach to the valves and help the valve stay shut during coronary or during ventricular systole or ventricular contraction. Now, once the blood has pooled into the right ventricle, it will eventually begin to contract, and then blood is forced out of the right ventricle through the pulmonary valve into the pulmonary trunk, where it is directed into pulmonary circulation. Okay. From there, the blood heads to the lungs, where it gets oxygenated and then returns to the heart via the pulmonary veins. Now, the left atrium is receiving oxygenated blood from pulmonary circulation. Now, you have, for the most part, you have, on average, 2 left and 2 right pulmonary veins, a superior and inferior on each. From the left atrium, blood moves into the left ventricle through the bicuspid valve. In general, the bicuspid valve is so called because it has 2 primary cusps, whereas the tricuspid has 3 primary cusps. The bicuspid is also sometimes referred to as your mitral valve. Once in the left ventricle, we have the same basic characteristics. We have the same trabeculae carnae. We have the same arrangement of papillary muscles. But here, because the bicuspid has only 2 cusps, we have only 2 papillary muscles. Again, they serve the same function that we saw in the, that we briefly mentioned in the right ventricle. Once the left ventricle is filled, it will contract, and it will send blood out of the through the aortic semilunar valve into the aorta, where blood is sent into or directed into systemic circulation. Excuse me. Where it will not only branch into the aorta, but eventually branch off into coronary circulation, as well as delivering all of that oxygenated blood to the tissues of your body. Now, one of the things you're going to notice is, depending on what part of the heart you're in, the thickness of your myocardial mass, the thickness of your muscle mass is going to be very different. And that's because the different regions of the heart are going to have different workloads. And just like the muscles of your body differ in strength depending on what their job is, so different strength and mass, I should say, so does the muscle mass of the heart. So if we first compare the atria to the ventricles, the workload of the atria is to pump blood from atria to ventricle, which is what, a couple inches, whereas the workload of the ventricles is to pump the blood out of the heart to the body. So the atrial walls by far don't need a lot of muscle mass to accomplish that very minimal task, so they're going to be very, very thin. The ventricular muscle mass, on the other hand, has to be much thicker. But even between the ventricles, we see a difference, and that's because the right ventricle we see here has to pump blood to the lungs, which again, not very far from the heart, whereas the left ventricle over here has to pump blood everywhere else, from the tips of your toes to the top of your head. As such, that left ventricle is going to require a lot more force to accomplish that. And so in order to generate that force, we need a much thicker muscle mass. Okay, so the left ventricle in particular is the largest muscle mass, and that's to accommodate the extra force necessary to direct blood throughout the body. Now, the heart, as we know, is made up of muscle, right? Well, if we compare the anatomy of or the functionality of the heart, I should say, to the functionality of skeletal muscle, well, let me ask you a question. Does skeletal muscle alone, all by itself, produce movement? Or let me rephrase that. Does skeletal muscle alone, independent of any other structure in your body, does skeletal muscle alone move your leg? Well, a lot of you might be thinking, well, yeah, but if you're thinking that, then you might be wondering, well, wait a minute, why the heck would she be asking such a stupid question? Well, think about it. Okay? Doesn't your muscle have to pull on something in order to move it? So you might think, oh, yeah, we also need a skeleton. Yeah, muscles need to be able to pull on something in order to create a movement. Well, the same is true for your heart. These cardiac muscle fibers have to be able to pull on something in order to get the necessary force and change in size and force to squeeze blood out of the heart, so to speak. So the heart, like the skeleton and bones and our skeleton serve as the anchoring point for our skeletal muscle, your heart also has its own skeleton. So what we're going to see is extended between all of your valves, we have this very thick fibrous connective tissue that is referred to as the fibrous skeleton of the heart. This tough fibrous connective tissue serves the purpose of anchoring those fibers, just like your skeleton serves as an anchoring point for your skeletal muscles. Now, this fibrous skeleton has some additional functions. We've already just talked about one, right? As it's an anchoring point. It's an anchoring point for that cardiac muscle. You also notice that this fibrous skeleton is also strategically placed between all four valves. So this skeleton also serves to support the valves. So these valves don't collapse every time this heart starts to contract, which kind of defeats the purpose, right? Because we need these valves to be open when the heart is contracting. The third function may not make a lot of sense yet, but it will a little later in our lecture. The third function of the heart, of this fibrous skeleton, is to serve as an electrical insulator. Now, what does that mean? Well, insulators are things that prevent the loss of something. So you have insulation in your house to prevent the loss of heat or cool air, right? And down here in Louisiana. You have plastic wrapped around a power cord to insulate it and keep the electrical signal inside of it. Well, what this means is this fibrous skeleton, which is found between the atria and the ventricle, as you can see, serves as an electrical insulator. So what it's going to do is stop electrical signals from moving between the atria and ventricles. Now, we'll see why this is important a little later in our lecture, but for now, that's as far as we're going to take it. Bringing us to our lovely heart valves. So what is the function of our heart valves? This is one of the more commonly misunderstood. This is one of the more commonly misunderstood functions of the valves in our heart. The function of a valve is not to allow blood to flow. This is no, no, no. And this statement here is false. The function of heart valves is actually to prevent the backflow of blood. Okay, so let's go ahead and see how this works. And I'm going to draw my little heart. I know, great heart, isn't it? Just a box. And now we're going to draw our wall separating the atria from the ventricles, and we're going to say that this is the left atrium and the left ventricle. Now, under normal circumstances, right, here's our bicuspid valve. We have blood moving from the left atrium to the left ventricle. Okay. Now, this happens when the atrium is contracting. Well, when the atria is done contracting, now the ventricles are going to contract, right? Let me go ahead and fix this diagram because I actually forgot something. Forgot our aorta, right? Now, once the left ventricle begins to contract, blood's going to want to start moving, but we don't want it to go in that direction. We want it to go that direction, which means we need to close that valve. So what we do is, what happens is blood gets caught in these cusps, and when blood gets caught in these cusps, they are forced closed like that. Now, this is great for low pressure situations, but here's the thing. The left atrium starts out at a pressure of around 20. So this valve is going to close as soon as the ventricular pressure reaches 21, because at that point, since the pressure in the ventricle is higher than the pressure in the atria, blood's going to want to go up. So the valve closes. But here's the thing. The resting pressure in our aorta is around 80, which means we're not going to have enough force to get that blood out of the left ventricle into the aorta until the pressure down here reaches 81, which means we're going to be hammering on that bicuspid valve for a long time before we can get that semilunar valve open. Well, if we keep hammering on this and hammering on this and hammering on this, what's going to happen to the valve? Well, it's going to flip open like that, or evert, which is bad. The question is, how do we prevent that? Well, if we're hammering and hammering and hammering on it, well, for every force we push on it this way, let's pull this way. That should keep it closed, right? Well, guess what? That is going to be the function of our chordae tendineae and our papillary muscles. Remember, we talked about those when we looked at the internal anatomy? what we see is with the tricuspid and bicuspid valves, the chordae tendineae, and then these guys are the papillary muscles. These guys are actually going to pull on the valve cusp. They're going to pull on the valve cusp in this direction. And the amount of force they pull in this direction is going to equal or counteract the force of the blood pushing on that valve in that direction. So what we see here is that we're now going to make sure that valve stays closed, and we're going to prevent it from everting or flipping in the other direction. And this is important because we're going to be hammering on that valve for quite a while, trying to get the pressure up high enough to eject the blood. Here we see some better images of your heart valves, and again, notice how in the ejected state, we are going to, these chordae tendineae are going to get tight, our papillary muscle is going to contract. This pulls the cusps down while the blood pushes it up, and they kind of counterbalance each other. Okay. Now that's not necessarily needed for our semilunar valves. For our semilunar valves, since they don't have that same opposing force like our that exists, between the ventricles and the atria, they just rely on the cusp method that you see here. So blood pools in these cusps and forces the three cusps together, and that serves its purpose efficiently. Now we have a couple of independent study sections, although we have actually already talked about them. I've already briefly mentioned systemic circulation and pulmonary circulation when I went over anatomy internal anatomy of the heart. But you do want to be familiar with the two as far as what structures are associated with each, so that I could actually give you a region of the heart as a starting point, and you could trace or tell me what structures come next based on blood flow through the heart. And then, and that's basically what's demonstrated here, showing you the ways in which blood flows through the heart. So this is kind of basically what you need to be familiar with. And finally, coronary circulation, another independent study section, so make sure you read through that on your own. Bringing us to some do you get it questions. So go ahead and pause your lecture, read through this, and let me know, and come back when you think you have the answer. So this would be a prime example of how knowing blood flow through the heart is necessary. So which one of these four lists them in the correct order? Hopefully you said C. Okay, C lists them in the right order. Pulmonary arteries carry oxygenated blood. True or false? Well, this gets a lot of students in trouble because they think arteries are oxygenated, arteries are red. Well, that's not actually the definition of an artery, and there are several exceptions to that. So instead, let's think about what the pulmonary arteries are doing. Well, the pulmonary arteries are carrying blood away from the heart to the lungs. If those pulmonary arteries are going to the lungs, are they already going to have oxygen? Well, no, they're going to be deoxygenated in order to get oxygen from the lungs. So pulmonary arteries actually carry deoxygenated blood, so this would be a false statement. Finally, a little bit of an application question, so read through this, pause if you need to, and see what you come up with. So a defective bicuspid valve would cause the blood to leak back into the, well, bicuspid, first question is that on the left side or the right side? That is on the left side, so that's hopefully going to eliminate A and C. The question is left atrium or left ventricle? Well, the bicuspid valve is to prevent backflow. So blood normally flows from left atrium to left ventricle. So if the bicuspid valve is not working, then blood is flowing backward back into the left atrium. And again, this is one students often pick the left ventricle because they think, again, valves are there to allow blood to flow, but that is not accurate. That is not correct. Valves prevent backflow. So that takes care of our first lecture on the cardiovascular system and the heart, and we'll come back and pick up with cardiac muscle histology later on with your next lecture.